This morning I had a thought, and I'm kicking myself for not having had this thought earlier. And the idea was to check into the ability of Sipser himself, because I do notice, I'm getting a stronger feel for what he considers worth explaining and what not. And my impression is that some things to him seem just so blindingly obvious he doesn't explain them. And whereas I think the average student at senior M1, first year master's level, the average student would not find such things obvious. So my suspicion was, he's probably a very bright guy, and it's not surprising because the text is pretty well classic, pretty much the Bible in terms of theory of computation. So I'm kicking myself for not checking on his credentials. So this morning I had a look at the beginning of the book, see if I could find out where he was based. If it was at some really good school, that would be a reflection on his ability. Well, it turns out he's at MIT, right? Massachusetts Institute of Technology, which is one of the top handful of schools on the planet. Okay, it's right up there with Cambridge University in England and Harvard University in the US and Berkeley. I mean, those three vie for top position in the world's most prestigious university year on year. It's again Harvard. I think the year before was Cambridge University and so on. So MIT is, I'd say, in the top five. Caltech, another major one. So, and I happen to know that if you're an undergrad and you want to get into MIT, you'll need a minimum IQ of about 160. Right? The competition is so stiff, and so few get in. What, a couple of hundred or something. I think Caltech, it's about 100 or so undergrads per year come in, freshers. So, extremely competitive. And he also, I noticed at the beginning of his text, he talks about, at the time he wrote this text, that he had been teaching this subject for about 15 years. And the book grew out of notes that the students had taken and given to him. And so eventually someone persuaded him to turn it into a proper book. So I can imagine then, if he's accustomed, up to 15, well, probably what, 20, 30, whatever. Let's see, when was the book written? What edition is it? It's the second edition. And what year was the second edition? 2006. Okay, right. Anyway, so after all those years, he's probably accustomed to pitching the level of detail of the explanation that would suit his 15 years of classes at MIT, right? So that would be consistent with the hypothesis I've been forming about the level of detail that he goes into, because he just leaves out quite a lot of the proofs. He just sort of throws stuff and assumes that you, the student, will have sufficient intelligence to be able to read between the lines, so to speak, to make the necessary deductions to arrive at the conclusion that he just throws at you. Okay. Now, in doing the third and fourth session of this board, I again got that impression. He just makes statements, and therefore, bloop, and huh? And then you have to, go fishing. You have to, like he's thrown something at you, and you have to deduce. It's not immediately obvious. You have to go, on a deduction trail to. You have to create your own little mini proof to see what he claims is actually true. And so, I thought that might be helpful. Making you aware that the author, Sipser, Michael Sipser, is an MIT professor, right, accustomed to MIT level students. And if you're a master's, because he says the text is aimed at seniors and first year masters. So there's a saying, you see, I stayed at a fraternity at MIT for a couple of months once, about 12 years ago, and the MIT students, they have a saying that a senior level class is equivalent to a master's just about anywhere else, and a first year master's class is almost like a PhD class anywhere else, well, except the other top schools, of course. So that goes a fair way in explaining my growing frustration. Right. Now, you remember the previous, the end of the last session, I was getting a bit confused about Sipser's derivation of the pumping length for context-free languages. And now, so I went back and looked at it, and I said I probably would. It's not surprising I was confused, because I think Sipser has just simply made a mistake, and I will fucking damn. Damn, I should have prepared this so I could get it quickly. Well, from memory, he gives two different formulas for the value of the pumping length. Now, I've got one at the bottom here. I'm just trying to find the other one. It was sort of let P be. Damn, when you want to find something, you can't. Oh, that's really annoying. What the hell is it? He gave two different values for the values of P, pumping length. And now when I want to find it, it just assumed to be trivial to find it, so I didn't. Oh, Jesus. Look, I'll give you one of them. At the bottom of the proof that we did on the previous board. So little b raised to power mod v plus 2 equals p. And from memory, he said that was toward the beginning of the proof, let p be equal to little b raised to power mod v. Plus 1. Yeah, plus 1. Where the... Oh, this is really annoying. Where did I see that? It's in there somewhere. So if I can't find it soon and just run out of patience, somewhere in the text, in the proof, there are two different values given for the pumping length. And so I promised you I'd explain in greater detail, because I found Sipser's explanation relatively unclear, and with a lot between the lines. And that would be consistent with him being an MIT prof, speaking to MIT undergrads and first year masters. Jesus Christ. Oh, here it is. Okay, it's in the actual proof. The first, at the beginning of near the beginning of the second paragraph. So the second paragraph reads: say mod v is the number of variables in G. We set little p, the pumping length, to be b to the mod v plus 1. Alright? Okay? And at the bottom, he has an expression, little b to the mod v plus 2. Now the exponent is mod v plus 2, and then he puts equals p. Well, that's just flat contradiction in my view. Okay? So I just went back to first principles and deduced it for myself, as if I were a MIT student taking his class, and I came out, the pumping lemma I came out would be this one, his second one. So I think his statement, his first one, it sounds plausible, but when you go into detail, it doesn't make sense. So B1. So I'll try now to explain how you calculate the pumping number, and from that deduce that the third condition. Remember in the pumping lemma, remember it was Vxy, the size of it, has to be less or equal to P. Well, this makes sense when you think of it in these pictorial form. Actually, I'm getting hot. I'm going to, for the last few days I've not switched on the air conditioning, but I'm starting to sweat, I can feel it. So I'm going to switch on the air conditioning. I'll need to close a few doors, so give me about 10 seconds. Okay, alright, so we're trying to choose a value for the pumping lemma, little p, so that all strings equal or larger than that length, p, little p, can be pumped. Alright? So, and the value that I'll get will be this one, which is one of the two given by Sipser, but this one makes more sense. Okay, so just one square. So we'll try and explain things. Now, the deeper your parse tree, common sense, the longer your string can be that you derive. Right. So the more steps you have, the more variables you have in a path. The wider and wider your string can be. That makes sense. Now, remember this mod v. What is that? What does it mean? It's the number of variables in your set, big V, in your grammar. Right? We're talking about a grammar. It's a parse tree. We're talking about a grammar. So mod v, the size of v, is the size of your set v. Which just means the number of elements that set has, which means the number of different variable symbols that grammar has. Okay, so that's